Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing Linear Algebra 1. This is Chapter 3, Geometric Vectors, Lines, and Planes. Specifically, Section 3.6 is going to be Lines and Planes in Space. 3.6.1 was describing lines and planes in space. 3.6.2, the previous video, was how to decide whether they're parallel, perpendicular, or neither in the 9 cases of whether it's 2 lines, 2 planes, or a line and a plane. And then basically what we're going to do is we'll give the scenario of whether we have to find out how they intersect each other, or if they're not and they're parallel, we're going to find out, actually we're going to do the scenario finding the distance between a point and a line and a point and a plane. But if you actually then rephrase the question saying find the distance between the 2 lines or the 2 planes, you find a point in one of the other ones and find the distance from that point to the other plane or something like that. So we'll describe this in gory detail. Let's get to it. All right, first of all, let's go over the overview of all the different scenarios that we can have in these ones so that you can think of where they're going to possibly give you these types of questions. The first thing they're going to do in the question probably is going to say, determine whether these 2 objects, 2 lines, 2 planes, or a line and a plane are parallel, perpendicular, or neither. There's 9 cases. Once you figure that out, we're going to say if they're parallel, that means they never interact, so we want to find the distance between them, whatever the objects are. And if they do interact, we want you to either find the point or line of intersection depending on which the objects are. So for intersections, we had 3 cases. When we compare 2 lines, it's going to be a point of intersection. If it's 2 planes intersect at a whole line of intersection. And if it's a line and a plane, those guys intersect in a point of intersection. So then we're going to have to decide how to, or figure out how to find the point of intersection of 2 lines, the line of intersection of 2 planes, which we're going to use linear algebra in a system and augment a matrix, find the general solution. And then in this one, we'll find the point of intersection, and it'll be similar to when do these functions intersect in calculus. When they're equations, we set them equal to each other, or when the equation of the line satisfies the equation of the plane, we plug it in, we find a parameter t, then we find parameter t, and we put it back, and we find a point of intersection. For distances between them, we're going to essentially actually look at 2 cases, and it'll cover all of these 3 cases. We're going to find out how to find the distance between a point and a line. So if you have 2 lines, you pick a point in the one line and find the distance between that point and the other line. And if you have a line and a plane, you can find a point in the plane and find the distance between that point and the line again. Or you can find a way of finding the distance between a point and a plane. And then if they say find the distance between the 2 planes, again, you find a point in one of the planes, you find the distance between that point and the other plane. So what we're going to do in this scenario actually is rephrase slightly and figure out how to find the distance between a point and a line and a point and a plane, so we can use that to find the distance between these types of objects. I know that's a little bit, they should unpack that somehow, or a wizard should do it in a video. Here we go. Alright, so we're going to do intersections first. There should be 3 cases, whether the 2 lines intersect, whether the 2 planes intersect, or whether a line and a plane intersect in 3 space. We had to cheat and get help with this one, but this is the one I've never really thought about that much. But if we're going to do that, first of all, just because the 2 lines are not parallel doesn't a priori in 3 space mean that they intersect. But if they do intersect, what we're going to have is you can put this in the symmetric avatar also, but I'll assume they put them in, or if you get the symmetric, put them back into the parametric avatar in there. I'm going to get 2 lines without loss of generality. They're both in symmetric or parametric form. Here they are. What that says is, if these intersect, that says that this xyz has to equal this xyz. So I set them equal to each other. Hypatia says if 2 things are equal to a third thing, they themselves are equal to each other. And then what I do is I'm phrasing this as a system of 3 equations and 2 unknowns. So I have 2 unknowns, s and t, in 3 equations. And what I'm trying to do is solve this linear system to find s and t such that I have a unique point of intersection of these 2 lines. So that's the general scenario of how to find the point of intersection of 2 lines in space. For 2 planes, without loss of generality, I'll give you the general form of the planes. And then literally what we're just going to do is I'm trying to find all x, y, z this time that are on both of these planes. I only have 2 equations in 3 unknowns now. So I'm automatically going to have a row of zeros. That means I have 1 free parameter, which will give me the general solution being a line through a point and in the direction of a vector, which is the parameterization, i.e. the solution to this will be the line and intersection of the 2 planes. And then in the last case, when I have a line and a plane, and notice I didn't draw any of the pictures, I'll do that for my examples when I actually start going to do it. But with I have a one-dimensional object intersecting with a two-dimensional object, it'll be a point of intersection. And now this one's slightly different, but what we're going to do is, again, without loss of general, I have the parametric form of the line and the general form of the plane. If you don't have those originally, put them in those forms, and then from this starting point, I know that this line, this xyz, has to satisfy the plane equation because that's where they intersect at that one point. So I put these xyz values into the equation of the plane. That will then give me one equation in t. Solve that one equation in one unknown for t. You'll get a t value. That t value I then put back into this equation, and I will find a three-dimensional point, which is the point of intersection of the line and the plane. So this is how we find intersections of objects in space. Let's do an example of each. All right, example one, let's find the intersection point of two lines in space. Here's the, like I said, I gave to myself, here's the two parametric avatars of these lines, L1 and L2. What we do is we set xyz equal to xyz. We're going to get a system of three equations in two unknowns. We're going to augment a matrix, row reduce, and find the unique solution. Those will give me the parameters. Once I use those parameters, I can use either the parameter t or the parameter s and put that in there to give me the point of intersection. Let's do that. What that's going to tell me is, when is this equal to this? This is going to tell me that 2 plus 6t 1 minus 8t negative 2 plus 10t is going to equal this guy, negative 1 plus 6s, negative 10 plus 7s, 5 minus 2s. I'm going to rearrange it. It's much nicer when you actually have numbers, not u1 and a, all those indices. Now they're gone. Not today, Satan. Put the numbers back in, except for our two parameters. Now what does that give me? I'll move these ones over, so I'm going to have 6t minus 6x equals negative 1 minus 2 is negative 3. Here I'm going to have negative 8t minus 7s equals negative 10 minus 1 is negative 11. And then here I'm going to have 10t plus 2s equals 5 plus 2 is 7. There's my system of three equations and two unknowns. If you want specifically, here's the unknown from the first one, and here's the unknown from the second one, s. I'm looking for s and t such that I have a unique solution to this system. How am I going to do that? It should be Pavlovian. Chapter 1, go back and look. I have a system of three equations and two unknowns. I'm going to augment a matrix. I'm going to get to REF, and I can decide whether I have one solution, no solution, infinitely many. It should be unique in this case. That's the point of intersection. What? You'll see. So I have an augmented matrix, 6, negative sex, negative sex. That's Freudian, not Pavlovian. 6 minus 3 equals negative 8, negative 7, negative 11. Is that all guys are talking about? Even when I try and do math. 10, 2, 7. What am I going to do with this? Regardless of what I'm thinking in the back of my brain, I need to Pavlovianly, not Freudianly, augment the matrix, row reduce, get a leading one, get zeros, get REF. So now what am I going to do? I'm going to be lazy, and well, my first move is just going to be divide the first row by 6. So I'm going to get 1, negative 1, negative 1/2. Now what I'm going to do is kill the 8 and kill the 10. So I have to multiply by positive 8. The first thing I'm going to do is copy down this row, 1, negative 1, negative 1/2, and then I'm going to get, what am I going to do? 8 minus 8 is 0, negative 7 minus 8 is negative 15, and then 11, oh wait, 8 divided by 2 is, then we're going to have a negative, so negative 4, oh, negative 15 also. Then what we're going to do is multiply by 10 this time, negative 10. And we're going to get 10 minus 10 is 0, what I wanted. 2 plus 10 is 12. And negative 10 times negative 1/2 is 5, plus 7 is 12. Well, that looks good. And then what am I going to do? I'm going to get that we have 1 minus 1 minus 1/2, 0, 1, 1, and 0, 0, 0. This is the one case where just because I got a row of zeros, that doesn't immediately mean I have infinitely many solutions. I should have a unique solution for s and t. And what is it going to say? You have a unique solution when the number of leading ones in row echelon form is equal to the number of unknowns you had originally. We have two unknowns, we have two leading ones. This is REF. Now I say, what does that say? That says S is equal to 1 and T minus S is equal to negative 1/2. So that says T is equal to negative 1/2 plus S, which is negative 1/2 plus 1, which is 1/2. So T is 1/2. This is the unique solution, but that's not the intersection point. I can use these to find the intersection point. What is that going to be? If I use that in, well, let's erase right here, let's say. And now if I want to use the T, what that says is X, Y, Z will equal. I have 2, 1, negative 2 plus 6 times 1/2 plus negative 8 times 1/2 and plus 10 times 1/2, which is equal to 2 plus 3, which is 5. This is equal to 1 minus 4, which is negative 3, and this is equal to negative 2 plus 5, which is 3. So our unique point of intersection is going to be this guy, which is X, Y, Z equals 5, negative 3, 3. This is the point of intersection. It has to have 3 coordinates because we're in dimension 3. Where do you get your coordinates from? The linear combination of a basis in that dimension. We'll get to that. We've already done those ones. So this is how you find the point of intersection of two lines in 3 space. Let's do the intersection of two planes, which is going to be a line of intersection. Example 2, we're going to find the line of intersection of the two-dimensional objects, the plane 1 and plane 2. So again, these are the general form of these two planes with the normal vector to P1, 1, negative 1, 3, that's correct. The coefficient standing in front of X, Y, Z in the general form. And this one is negative 2, 0, 1. I just couldn't help myself pointing that out. What are we going to do here? This is literally, we're saying, find all X, Y, Z points in 3 space that are on this plane and all points that are on this plane simultaneously, or find that line of intersection. We already have this. What that says is solve this linear system and solve this one, negative 2x plus z equals 4. I bring the 4 to the other side. So this is 2 equations in 3 unknowns. So I have a 2 by 3 system. I'm going to augment the matrix, row reduce, get to REF, and then the infinite many solutions will be the line of intersection of the two planes. So what is that going to give me? This is going to give me 1 minus 1, 3 equals 0, negative 2, 0, 1 equals 4. I have a leading 1, good, I need to get rid of this. We're going to multiply by 2 and add. I'm going to get 1 minus 1, 3 equals 0. Negative 2 plus 2 is 0. 0 plus negative 2 is negative 2. 1 plus 6 is 7. And 4 plus 0 is 4. Now what can I do with that? Essentially that already gives us the horrible, what is this REF? I'm going to go one more, but I have to have the fractions. There's no way out of it. This is going to give me, by dividing by negative 1/2, I'm going to have, or dividing by 2, negative 2. I'm going to get this, and then I'm going to have 0, 1, negative 7 over 2, negative 2. This is now REF. So is this, but I like this one a little more. I already secretly, because we only had one, it was underdetermined already, we already have a row of zeros. That says we're going to have infinitely many solutions. Which one can I make the free variable? The variable that didn't have a leading entry. So I'm going to let z be free. And then we're going to let this says y minus 7 over 2 t equals negative 2. So that says y equals negative 2 plus 7 over 2t. And then this equation says that x is equal to y minus 3z, which is equal to, now I have to squeeze that in there, y was negative 2 plus 7 over 2t, and then minus 3 times z, which is t. So that gives me 3.5 minus 3, which says that x is negative 2, again, plus t over 2, if I did that correctly. What does that say? That says that our infinitely many solutions are x equals negative 2 plus 1/2 t, y is equal to negative 2 plus 7 over 2t, and z is equal to 0 plus 1 times t. And what is that? That's the parametric form of a line in space. So this is, in fact, the line of intersection of those two planes. But geometrically, solving this system of two equations in three unknowns is going to have infinitely many solutions. Those infinitely many solutions, every point on there is then on the line of the intersection of those two planes. Let's do the intersection of a line and a plane now. Again, in this one, example 3, we're going to find the intersection in the anti-Goldilocks land of a one-dimensional line and a two-dimensional plane. Again, first of all, the picture technically is going to be, here's the plane P, and then we have a line L, which either means that it's oblique or perpendicular. I don't know which one. You can go back and look at the other video to determine whether they're parallel or perpendicular or neither. But regardless, we're going to assume that they've already checked, and that says that we know that it's either oblique or perpendicular, so therefore there is an intersection point. What I want to do, ooh la la, it's like, that's not what we meant. There it is. It's like, there it is. It's like, no, you have to algebraically find it. In this scenario, what we're going to say is the line has infinitely many points on it and the plane has infinitely many points on it, but there's a unique point which is both on the line and on the plane. There it is. How do I find it algebraically? These guys are going to satisfy the plane's equation. So I put x equals this guy into here. We don't have a y because I wanted it simple for myself, but then I put the z into here, and then we have one equation in one unknown. Go back to our first videos. This is how you systematically solve one equation in one unknown. Once I have the parameter t is not the point. I use the parameter t and put it back into the parametric equations of the line to give me the unique three-dimensional point, which is the intersection of the line and the plane. So step 1, put the parametric equations of the line into the general form of the plane. This says that x, which is 2 plus 3t, plus z, which is negative 1 plus 8t, minus 3 equals 0. Now I have one equation and one unknown t. What am I going to do? Group like terms. What do I have? I have 2 minus 4 plus 3t plus 8t equals 0. So that's going to give me 11t equals, this is negative 2, I bring it over, 2. Oh, so we got horrible fractions. This says t is equal to 2 over 11. That's not the point though. That's the parameter value at which the three-dimensional point in these equations will intersect the plane P. So what do I have to do with that? Unfortunately, 2 over 11 I have to put in here and then simplify or make you do it as an exercise. Probably the latter. We'll see. So what does that mean? Putting that back in there, the unique point x naught, y naught, z naught, which is their intersection point, will be putting this parameter back into here. I'm going to get 2 plus 3 times 2 over 11, 4 minus 4 times 2 over 11, and negative 1 plus 8 times 2 over 11, which is what? How do we add fractions? This is 2 times 11 over 11 plus 6 over 11. This one is equal to 4 times 11 over 11 minus 8 over 11. And this one is equal to negative 1 times 11 over 11 plus 16 over 11. So this will be, what, 28 over 11. This one will be 44 minus 8. Well, that's going to be what? 36 over 11. Are those in lowest terms? Yes. And then this one is going to be what? 16 minus 11, which will be 5 over 11. This is the point of intersection. So our unique point is 20, or we could write it as 1 over 11, 28, 35. That's the point of intersection. Now let's do, if they don't intersect, they must be parallel to each other. Let's find the distance between these. How we're going to phrase this is we're going to find the distance between a point and a line and a point and a plane. Then regardless of the scenarios they give you, pick a point in one of the objects, find the distance from that point to the other object. All right, distance from a point A, x1, y1, z1 to a line. I don't know why I put the coordinates in there. I'm not going to give you the horrible detail because if I give you the algebraic formula, it'll please me thoroughly and you'll be like, I'm never going to memorize that. Don't. You're going to memorize how to draw the picture and how to derive the orthogonal complement of the projection of AB onto V, and then that's still not the whole story. The distance between them is the length of this. So the length of W is the distance we're looking for. This is the distance between the point A external from the line and the line. We have to find the shortest distance between an external point and a line from Euclidean geometry is the perpendicular dropped from the point A to our line L. in our horrible notation, or extremely useful notation and compact notation, what that's going to be is the norm of the vector, which is going to be our distance, is w. Who is w, or omega? It's the orthogonal complement of the vector AB projected onto v. So how am I doing this? First, I have a line and a point. That's what you actually have to start with. And what I have to do is, this is going to be the distance. How am I going to construct that? First, I have to find an arbitrary point on my line L, which I'm going to call B. Then I'm going to create the vector AB. Then I already know in the direction somewhere of my line is a vector V. I'm going to orthogonally project AB onto V to create P, who is the projection of AB onto V. But that's not what I want. I want this vector. That vector is W. W is AB minus the projection of AB onto V as a vector. And then finally, I won't write out what that algebraically looks like. You can go into the coordinates of everybody, but it's horrible. We'll just memorize this. Our distance is the length of W, which is the norm, or the orthogonal complement of the projection of AB onto V. So this is AB minus the projection of AB onto V. Applications of orthogonal complements and projections, finding the distance between a point and a line. You're like, that was all mumbo jumbo. Okay, we'll get rid of half of it, and we're going to put numbers in there, and you'll see that this will all be a calculation, and that's the norm. We've already done these things. Find the vector, then calculate its length. That is the distance between the external point and the line. All right, example 4, what we're going to do is find the distance between this external point A and the line given by these parametric equations, 3 minus t, 1 plus t, and 1. What are we going to do? First, we're going to please mark the mark gods, the Solomonovich gods, and draw a picture. There's the line L arbitrarily, and what does it say? I have an external point A. So then what do I want to do? And that's why the picture helps me, and because I can use this to, what point B should I pick? There's a point B already on there. It gives it to me in the parametric form, but I need a point B on my line L. And you're like, where am I going to get that? That TB0, 311 is a point on my plane, or on my line. Then, so what does that say? A, they already told me, was 1, 0, 2. B now, how do I find a point B? Set the parameter t equals 0. That will give you a point. So then that gives me 3, 1, 1. Now I have a point AB. I have to create the vector AB, which is A minus B. I just wrote it backwards. Did I draw that backwards the whole time? This guy is BA. So in my derivation, it was backwards the whole time. But what is that? That's A minus B as geometric vectors, which is going to be what now? This should be 1, 0, 2 minus 3, 1, 1. It doesn't really matter. If you did the other vector, it would just be the negative of that vector. But technically in my picture, I'm just going to draw that one for simplicity, and orthogonally project, then find the complement. So this is equal to 1 minus 3, 0 minus 1, 2 minus 1, which is equal to negative 2, negative 1, 1. So now I have BA, not AB. Doesn't really matter. What do I do with that now? That is, now I have to project that vector onto a vector in the direction of my line L. Who is that going to be? Well, V, it turns out, is going to be the vector with coordinates negative 1, 1, 0, standing in front of the parameter in here. So now what I have to do is orthogonally project this onto this. So that says that the projection of BA onto V is going to be equal to, how do I do this as vectors? This is BA dot product V over the norm of V squared times V. This is going to give me, first of all, BA was negative 2, negative 1, 1. So what I'm going to do is, first of all, I have to create BA dot product V. That is going to be negative 2 times negative 1 plus 1 times negative 1 plus 0 times 1, which is going to give me 2 minus 1, which is 1. Then I'm going to compute the norm of V squared. The norm of V squared is going to be negative 1 squared plus 1 squared plus 0 squared, which is 2. Therefore, this says that the projection of BA onto V is going to be BA dot V, which was 1 over the norm of V squared, which is 2, which is going to be therefore times v, which is negative 1, 1, 0. That is the orthogonal projection of BA onto V, but that's not the vector we want. We want W. W is BA minus this projection. So how do I get that? Our vector W is going to be BA minus the projection of BA onto V, which is going to equal what? BA was, I just erased it, negative 2, negative 1, 1, minus negative 1/2, 1/2, 0. I put the scalar multiple in. What is that going to give me? That's going to give me negative 2 plus 1/2, which is negative 3 over 2. This is negative 1 minus 1/2, which is negative 3 over 2. And this is 1 minus 0, which is 1. So now this is our vector W, which is the orthogonal complement of the projection of BA onto V. But that's a three-dimensional vector in space. The length of that, or the norm, is the distance. So the norm of W is the distance D I'm looking for. So D is going to be the norm of W, which is going to be the norm of, you don't have to put it in that horrible algebra, it's the norm of this guy, negative 3 over 2, negative 3 over 2, 1, which is going to be what? The square root of negative 3 over 2 squared plus negative 3 over 2 squared plus 1 squared, which is equal to, what am I going to get? The square root of 9 over 2 plus 9 over 4, 9 over 4 plus 4 over 4, which is 18, 19, 20, 21, 22, which is the square root of 22 over 2. There's the distance. Don't expect those to be nice numbers, but this is the distance between that external point A and the line L. Now let's do the distance between a point and a plane. That one actually turns out to be an easier formula to memorize. I can even give you a clever algebraic deduction. I'm still going to draw a picture and derive it every time, so here we go. All right, let's find the distance, or derive how we compute the distance between an external point A and a plane P this time. So I have this point A, which, if you ignore the vectors at first, is just a point by itself in space, and I want to find the distance between A and the plane. Again, it's going to be the perpendicular drop, so this D. What I also know is I can construct the normal vector of that plane, and any one of these vectors is the normal vector. As long as it has the same magnitude and the same direction, vectors are equal. So all those guys are, so just make it so that the normal vector goes through that point A, and then what we have to do is from that point A, find another point B in the plane. How we're going to do that, I'll show you in a second. Just find x, y, z, which satisfy the equation of the plane. Then I have a point in the plane. Then I'm going to construct the vector, it's correct this time, A to B, so we're going to create the vector AB. Then I'm going to orthogonally project this vector AB onto N, and then the length of that will be our distance D. What is that saying? First of all, I'm going to create the vector U, which is AB. Then what I'm going to do is I'm going to create a vector A, which is the projection of U onto my normal vector N. Then what that says now is our distance, which was in pink, apparently not blue, D is equal to the length of A, which is equal to the length of the projection of U onto V, which is going to be, actually let's keep that as AB, which is going to be what? That is the length of, how do I find the projection? That will be AB dot product N, that should be an N, over the norm of N squared times N, which is, this is a number, so you can take it out in absolute value, which is unfortunate that it's absolute value, times norm of N over norm of N squared. One of these is going to cancel, and so we get a clever formula. This will be the absolute value of A dot B, or AB dot N, over the norm of N. That's absolute value. Again, what I'm going to do every time is derive the, or draw the picture, and then derive from that what the distance is. But if you really want, skip the middleman and write down the distance. How are we going to do this? I take the point A, I find a point in the plane, I create the vector AB, I orthogonally project AB onto N, which is going to give me that formula. Or once you create A, what you're going to do is create the dot product of A and N, and you're going to find the length of N. The ratio of that is the distance. Let's do that at least once in an example. All right, the home stretch, and then I'll wave a hand at, we're going to do one more video when we make much more complicated problems out of this, where I'll make you decide whether they're parallel, perpendicular, or neither, and then if they are, based on that, if they're parallel, find the distance between the objects. If they're perpendicular or neither, find the intersection of the objects in some way, shape, or form. How do I find the distance between an external point and a plane this time? That's correct. I draw a picture. Here's the plane P. And then I have an external. Now you can see the derivation from the already pre-cooked up one that I had before. Then I have an external point A. What I need to do is find this distance D to the plane. But to do that, I first have to create and find a point B in my plane. Once I do that, I create the vector AB. Then I do the business of finding the distance, which is going to be, what is the distance every time? It will be the absolute value of AB dot product with the normal vector over the norm of the normal vector in absolute value. You might get a negative and distance is positive, which is exactly what happens here. That's why I've done it. So, this is our formula. You have to memorize or derive every time. How am I actually getting this? Step one is find a point. So I have A is equal to 3, negative 1, 5. Then I need a point B. How am I going to do that? I need a point X, Y, Z that's on this plane. If I let X equal 0 and Y equals 0, that says Z is 1. So a point on there is 0, 0, 1. That's an extremely good way of finding a point on a plane. Let two of the coordinates be 0, and now I have one equation and one unknown, solve for Z. That means if X is 0 and Y is 0 and Z is 1, that gives me exactly 2. Oh, that will work. So that's a point on my plane. I don't want crazy anyways. That's good for me. I like zeros. Now what do I have to do? Now I have to create the vector U, which is AB, which is B minus A as coordinates, which is going to be 0, 0, 1 minus 3, negative 1, 5, which is going to be negative 3, 1, negative 4. Once I have that, now what am I going to do? I'm going to find the norm of the orthogonal projection of AB onto the normal vector. Who's the normal vector? The coefficient standing in front of the x, y, z in normal, or in general form. So this should be 2, negative 1, 2. Now I have AB and I have N. Let's create the projection of AB onto N as a vector. That's going to be AB dot N over the norm of N squared times N. And the length of that is our distance. So how are we going to do that? That is going to be what is the dot product of AB dot N. This will be, so first of all, how am I going to clean this up? Let's erase that and move it up. So once I have AB and I have my normal vector, what am I going to do with that? I have to find the projection of AB onto N. So first of all, I need AB dot product with N. What is that going to be? Negative 3, 1, negative 4 dot product with 2, negative 1, 2, which is going to be negative 6 minus 1 minus 8, which is negative 15. That's where we're going to need the absolute value. And then what do I need? I need the norm of N. Technically speaking, if you're going to memorize the formula now, what's the norm of N? This is going to be the square root of 2 squared plus negative 1 squared plus 2 squared, which is the square root of, there's a Pythagorean triple, or quadruple. Anyways, what did that give me? 4 plus 4 and plus 1 is 9, so the square root of 9, which is 3. And so that says that the distance is equal to the absolute value of A, B dot N over the norm of N, which is equal to the absolute value of negative 15 over 3, which is the absolute value of negative 5, which is 5. The distance between them is the integer 5. That's not going to happen in usual, so it's probably going to be a square root in there somewhere from here. But this is how we find the distance between a point and a plane. Now, if I have, I'll use this guy as my line. So if I now have I have to use these two scenarios for the distance between a point and a line or a point and a plane to actually ask the question, how do I find the distance between two lines, two planes, or a line and a plane? So if I have two lines, what I'm going to do is pick a point in one of the lines and then find the distance between the point and the line. If I have two planes, I'm going to find a point in one of the planes and find the distance between that point and the other plane. If I have a line and a plane, it's harder to find the distance between the point in the line than it is the point in the plane. So I'll pick the point in the line and then find the distance between that point to the plane. So I'm going to use these two scenarios to do the other three scenarios of finding the distance between the actual geometric objects. We'll do that next time when we do a video on first giving you problems where it says in many different scenarios you can see of first comparing lines and planes and whether they're parallel, perpendicular, or neither. And then we're going to give you follow-ups that say if they are parallel, find the distance between them. If they are not parallel, that means they intersect in some way, and we need to find how they intersect, either the line or point of intersection. Please subscribe right here. I'll see you next time. That deserves a multiple mic drop.